Systems. So I start you off here with an image of a very complicated system. And we're not going to do anything that crazy. We have to be honest and say we don't understand everything about climate change yet. We're going to spend a lot of time next semester on climate change. It's really the whole point of this course. But when we study climate change, look what goes into it. Everything from volcanoes on the left, the sun, obviously, which provides energy on Earth. And each of these is what, in a system, we call these a stock. And a stock is something that is able to change. Oh, that sounds like the Lorax, right? We wrote a list of things that change. Those are stocks. And so we look at the relationships, you know, is one going up, is one going down? Just like we did yesterday. We look for feedback. We look for loops that are either growing exponentially or are canceling each other out and balancing positive and negative feedback. So that's what a system is. It's these relationships. And you change one little piece of this complicated system and you can screw up everything else. So when we look at something like land use or human activities on the right, is it possible that humans could drastically screw up the climate? Absolutely. You know, and one of these little changes could be a big problem down the road. We can first classify a system as being either open or closed. Now, you have to be careful what we're referring to here. I've given you some classic examples. An island would be considered an open system, and a submarine would be considered a closed system. Now, I like to think about it as, do you have the materials that are needed to keep you alive? If not, can you get more easily? If you are on an island and you run out of food or fresh water, are there ways to get more? Well, you could go fish, right? You could get fish that can come to the island, swim to it and catch them. You could wait for it to rain. You could catch the rainwater and you would have fresh water to drink again. So as long as weather and biodiversity did its thing, you'd be okay. Now, when you board a submarine and you leave the dock and you are out in the middle of the ocean, everything you need to keep you alive must be on that ship. Because there is no little convenience store gas station at the bottom of the ocean where you can stop and say, hey, I ran out of chips. There's no oxygen tank down there to refill if you have a problem. We're talking about matter. Can matter get in or out of the system? If matter can get in, then it's considered open. Or if matter can get out. If it can't, then it's closed. Now, don't confuse matter and energy, because energy, by definition, actually has to be able to get in and out of a system. If it didn't, then the system would probably overload or overheat. Energy can go in and out of either of them, but not matter. All right, if you understand all of that, you should be able to answer my next question. Is the Earth an open system or a closed system? Open, 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 open. You're all saying open. You all are wrong. There we go. Closed, closed, closed. Both. Yes. All right. So technically, the Earth is both. It really represents, though, most Earth scientists will tell you that the Earth is considered closed. Think about this. We have all the things on our planet to keep us alive, right? If we run out of them, where do we stop by and get more? We don't. So we are literally a submarine in space. Do you ever think of it that way? We are a ship floating in the middle of a giant ocean of nothing. That's what the Earth is. So we're considered closed. Now, you could argue that we're open because there is some matter that moves in and out. Meteors are one example. Another example would be astronauts, right? We have been to the moon. We've sent spacecraft to different planets and moons. So technically, we're making the Earth more open with our technology, but in reality, we're considered a closed system.
So I have a question.
Yeah.
Couldn't the whole universe be considered a closed system too? Because we
Ah,
don't know if it's
by
that's
our
all.
definitions, the universe would be a closed system. Yep. Very deep. Way to go. I like when kids ask questions like that. Okay. This one I'm not too concerned about, but the Earth is considered a dynamic system. And we're going to dive right into that next week when we look at something called plate tectonics. The Earth is not just a rock that's unchanging. Our Earth changes significantly. We experience that through earthquakes, volcanoes, but really that's the theory of tectonics. So we are dynamic, which means able to change. A system that is stable or is really completely closed can sometimes become static, which means unchanging. So think of a balloon that is tied off. You know, eventually the air is going to leak out and it's going to deflate, but that balloon will stay stable for a period of time. A dynamic system, hot air balloon, can go up or down based on the temperature of the air in the balloon. A stock is anything that can change in the system. So you are a stock. You are a member of a population which can go up or down. And things that make you go up or down are called, usually up, are called inputs. And so the input for the human population system would be births, having new humans be born. The output would be deaths, having things removed from the system. So those are the basic terms we use. Input is when we get more of something. The stock is what we're measuring, what's changing. And the output is when something leaves the system or dies. So here you see that sunlight is an input to allow plants to grow. They die when they get eaten by a primary consumer. That primary consumer populates. It dies when it gets eaten by a secondary consumer. If you don't remember those terms, we'll get into all that in the ecology unit. Inputs, outputs, birth and death, populations change size. I'm never going to ask you this equation. You don't need to write it down or anything. But the size of the stock, the change in the stock, is simply just the input, the births, minus the deaths. That makes sense. Whatever goes in, if you look at the first example, the arrow on the left is fatter, darker, and the arrow on the right is thinner. So that means your input is greater than your output. If that happens, your population will grow. More births than deaths, population gets bigger. It's common sense. On the middle example, the output is bigger. So the deaths outnumber the births, and your population would shrink in size. And finally, if your births and deaths are equal and cancel each other out, then your population does not change. The stock would be constant. Average residence time. This is how long something stays in a system. From the time that it is input to the time that it is output. How long was it in the stock? And it can be factored by how much space you have, that's S, and how fast things flow out of the system, into or out of the system. So if you have have you ever taken your thumb, put it over the end of a hose and the water sprays out, right? You can kind of speed up or slow down the water coming in or out. So depending on the size of your stream, you could have a lake growing or a lake shrinking. That's why we build a dam. A dam controls the outflow, and we can then have a reservoir that we use for recreation, drinking water, electricity, all that good stuff. You have art. All it is your life expectancy. How long are you going to be alive? How long are you going to be in this population? That is your average residence time. How long will you live on Earth? I'm going to stop there today. We'll do another little chunk tomorrow, and I will have some practice questions for you tomorrow after the lesson. Good to see you. Have a wonderful Thursday.